need to show you guys how to do a roller coaster problem. It's important to know that most of the time, the roller coaster problems that we do in class are going to be frictionless. That means it's a totally conservative system. And so one of the things that we have to keep in mind with a totally conservative system is that there is no heat loss because of friction. So we can write an equation for all of total energy that looks like this. Total energy is equal to the sum of all the different types of energy, right? So we have mechanical energy. We have electrical energy. We have heat energy. We have chemical energy. We have light energy. And that's 1, 2, 3, 4, 5 different forms. You can add nuclear in too for a sixth form. But like I said, I usually lump it in with chemical. But in a totally conservative system, right, the only conversions of energy you have are between potential energy and kinetic energy. So that's what mechanical energy is made up of. It is just PE and KE. And there are no other forms of energy. There's no heat loss. There's no electricity produced. There's no chemical energy produced. There's no light energy produced. So all you're left with is total energy equals PE plus KE. Okay. Then you also know the PE equation is mgh. And the KE equation is 1/2 mv squared. And to do this entire problem, that's all you need to know is those three equations right here. These three are very, very important. So if you ever have one of these, you can get the other. If you have the other, then you can get something else. Okay, and I'll show you how to do that. So to set this problem up, I'll tell you how it'll be worded. You have a crane that lifts a cart up a hill. In this case, it's a 65-meter tall hill and puts it at the top of the track at point A. From point A, it just begins to roll down the track, and it rolls down the frictionless track all the way down 65 meters to point B, where it's at the very, very bottom. And then it rolls back up a hill. And then at point C, I want to figure out what height it is. I've got to tell you a velocity here. I forgot to put that velocity. Let's make it 18 meters per second. All right. And then you'll know velocity, so you get height at point C. And then that's what I'm going to ask you to do is fill out this table right here at points A, B, and C. I want to know all these things. I want to know total energy at every point. I want to know potential energy at every point, kinetic, the height, and the velocity at every single point A, B, and C. It doesn't matter what goes on between A and C or anything, as long as you know a couple of things, you'll be able to do it. But this is a very simple version of the problem. Okay, so the first thing I have to ask myself is how much work has been done to this cart to pull it up 65 meters. Okay, so I had to lift the cart up. So work is force times distance. So I had to lift the cart up 65 meters. I know that's 65, but I had to do that by applying some sort of force to it. Now the force is the weight of the cart, not the mass of the cart, the weight of it. So the weight of the cart, Fg, is mg, which is 1,000 times 9.8. All right, so we can say that that's 9,800 newtons. So if I do this math, I get 637,000. So 637,000 joules. 637,000 joules worth of work to pull the cart from the bottom to the top. So if I did that much work to it, that's the amount of energy I gave it. Okay, so the amount of work you do is the total energy. So my total energy at point A is 637,000 joules. But in a conservative system, we never lose energy to something that we're not using, like heat. So the total energy is always going to remain the same no matter where you are on the track. And that is super crazy important. So if I gave it 637,000 joules worth of work, then no matter where you are, it has a total of 637,000 joules of energy. So 637 for all points and any points in between. All right, now I want to calculate my potential energy. So my potential energy is mgh everywhere. So if I wanted to calculate potential energy at A, it's PE equals mgh. Well, if you paid attention, you might notice something. M is 1,000, G is 9.8, and H is 65. What do we get here? We get 637,000 joules. So the potential energy at point A is also 637,000 joules. At point B, we also calculate potential energy as mgh. But what's H at B? And you might notice, well, it's at ground level, so it's 0 meters above the ground. That is correct. So it doesn't matter what mg is. If H is 0, PE is going to be 0. So at point B, potential energy is 0 joules. And at point C, to calculate potential energy, we also do mgh. But we have a problem because we don't know the height. So we're not going to be able to get it off of this equation. It's going to be something different. So we'll leave that blank for right now. All right, now we move to kinetic energies. So kinetic energies everywhere. So if kinetic energy is 1/2 mv squared, at the very top up here at A, just as it's beginning to roll down the hill, we can say that the velocity is 0. It wasn't given an initial push. Gravity's just kind of taking it there. Okay, so if velocity is 0, our kinetic energy is 0 here at point A. But how fast is it going down here? We don't know. We know it's picked up speed and it's going some sort of speed down here, but we don't know it. But if we go back to where total is equal to PE plus KE, then we can say our total energy here is 637,000 joules. We know the potential energy is 0. So the kinetic energy must be 637,000 joules. So if you look at this table, look what's happened between the max height at A and the minimum height at B. The kinetic energy and the potential energy have flip-flopped. Okay, so that's exactly what happens conceptually. Now you have all potential and no kinetic, but as you fall down the hill, you're losing potential energy because you're getting lower, your distance is smaller, but you're gaining kinetic because your speed is getting bigger. And down here at the bottom, you have the biggest speed that you're ever going to have, so your kinetic energy has to be at a max. So that's why we have a max kinetic energy down here and a minimum potential energy here at B, and they're just flip-flopped from point A. Okay, so moving on to point C. Since we have a velocity, that's pretty easy to get kinetic energy there. So you just take 1/2 times 1,000 and multiply it by 18 squared. Don't forget to square that 18. It's a commonly missed thing. So 500 times 18 squared is 162,000. 162,000 joules worth of kinetic energy here. 162,000 joules. And now we've got something right here. The potential energy. We still know at point C, at point B, at point A, at any intermediary point in between, that total energy is kinetic plus potential. So at point C, if total is 637,000, and it is equal to potential plus kinetic, and we know kinetic is 162,000, we can just subtract 637,000 minus 162,000, and we get 475,000. So our potential energy here is 475,000 joules. That plus that potential plus kinetic is equal to the total. All right, now here's some easy ones. The first two are really easy. At point A, the height I gave to you was 65 meters. And the height at B is 0 meters because it's at ground level. The velocity at A was 0. But we don't know the velocity at B. We do know the velocity at C. I can go ahead and say that that's 18. And so we are left with the velocity at B and the height at C. So if I know my kinetic energy, I can always find my velocity. So my kinetic energy at point B was 637,000 joules. So I just plug 637,000 in for kinetic. 1/2 times 1,000 times V squared. So I take my 637,000, I divide it by 500, and then I take the square root of that number, and I get 35.7 meters per second. So the velocity at B is 35.7 meters per second. This is the fastest it's ever going to move. And we know that it slows down, slows down, and slows down. And it's going to be slower at point C than it is at point B. And that makes sense because it's 18 at point C from 35.7 at point B. And now we got to calculate the height at point C. So to do that, we use potential because potential has the height term in it. So we know the potential at B because we calculated, I'm sorry, the potential at C, we calculated that to be 475,000. And that equals to 1,000 times 9.8 times H. So I solve for H. 475,000 divided by 9,800. And I get 48.47 meters high. So 48 just call it 5 meters, which makes sense. We know that C has to be under this height because if you think about what the cart's going to do as it goes past C, it's going 18 meters per second. So it's going to end up going past C and slow down to 0. If there is no friction, no heat loss, it's going to get all the way back up to here, which is 65 meters high, which is the same as this. And then it's going to stop, which means kinetic energy is 0, potential energy is at a maximum, and total energy is 637. So that means potential would be 637 all the way up here. And then it's going to roll back down, where it's going to pick up speed, get up to this speed right here at 35.7, get slower as it goes up, stop, come back down, and just kind of repeat that pattern for forever. If the track is frictionless. We know that doesn't happen in real life. We have friction going on, so it dampens a little bit. It doesn't quite get up that high. And then it just kind of like slows down and finally settles down here at the bottom. But we're not having any heat loss because of friction in this problem, so it's going to do this for forever. Okay, so if we want to create an analogy, which I think is something that might be helpful for some people, the analogy is height is to potential energy as velocity is to kinetic energy. So whenever I want a height, I need to use potential energy and mgh to do that. If I ever need velocity, I need kinetic energy and use 1/2 mv squared to do that. Right. So keep that in mind when you do it. And I think you'll be able to do any problem like this. Now, like I said, it doesn't matter what happens in the middle here. I could have a hump like this, and if I knew the height of that hump, I could just find the potential and the kinetic there and then solve for the velocity to see how fast it was going. I could put in a loop, right? And at this point right here, I know the height, and I could calculate the potential energy, which would give me the kinetic energy, which I could get the velocity. If I got velocity, I can say that that's my tangential velocity, and then use that equation in a vertical circle and see if my cart was going fast enough for this loop, just like we did in class with vertical circles and all that kind of stuff. So like I said, it doesn't matter what goes on in the middle here. You approach the problem the exact same way. All right, so I'll give you one of these to do on your own. I hope this helps. Go back and look at the process of me doing this. And I know I went through it pretty fast, but you can always go back and look, and hope it helps. And let me know if you got any questions.